Hello, in this video we're going to continue our discussion on Algebra 2 for this new semester. We're covering Chapter 2, Part 3 in this video about linear functions and the slope-intercept form. Again, this should be a review for most students in Algebra 2, but I wanted to make sure that we're all on the same page before we move forward, so here we go. The objectives for this video and lesson is to graph linear equations and to write different equations of lines. We have some vocabulary we need to be familiar with: slope, x-intercept, y-intercept, slope-intercept form of a linear equation. The Common Core standards that we plan to cover are also listed here if you'd like to look them up on your own. So generally speaking, points in a coordinate grid are described by indicating horizontal and vertical distances from a starting point, which we call our origin. Lots of you are familiar with the XY Cartesian coordinate system, and if we start from the origin, we can move in some horizontal direction and some vertical direction, and that's going to place a coordinate for us, or a position of the graph. When the points in a coordinate grid follow a well-defined pattern, usually an equation or a formula can be used to describe that pattern, and a line or sometimes a curve is produced by plotting all of the points. So if I have a single point, that's just a dot in space, but if I have several points that follow a particular pattern, we could draw several of those points, or more often we'll actually draw a line or a curve that connects those points, and that represents all points or coordinates that satisfy the particular equation. So when we're talking about straight lines or linear equations, we would say that the slope of a non-vertical line is the ratio or fraction. Ratio is another word for fraction of the vertical change, which we will call the rise, and the horizontal change or the run between any two points. So if I picked 2 points that lived on a line and calculated the vertical change, the rise, and the horizontal change, the run, that ratio or the fraction that's created by that is what we would call our slope. What's interesting is that I could pick any 2 points on a straight line and calculate the ratio, and the ratio will be exactly the same. Now, the amount of rise here and the amount of run here is less than the example that we saw originally, but the claim here is that the ratio itself, when the fraction is reduced, they will be the same. So the actual numerical values might be different, but the ratio itself becomes exactly the same. So in function form, we would say something like this, or as an equation, we would say that the slope is equal to the vertical change divided by the horizontal change, the rise divided by the run. And more commonly, we write the equation when we have 2 coordinates, an x1 and x1 and y1 component and an x2 and a y2 component of an equation. We would write our vertical change this way: y2 minus y1. And the horizontal change this way, x2 minus x1. We pick the x and y coordinates from the 2 points in the graph. And if we were to divide those two, we'll get either a number or a reduced fraction. And that number or reduced fraction we generally assign to the letter m, or we recognize it as the letter m. Not 100% sure where the letter m comes from, why m represents slope, but it is common and it's ubiquitous in math class. So if you see an m value, we should recognize that we are talking about a slope. So, for example, what is the slope of the line that passes through these given points? And does the order matter when using the slope formula? And finally, which of these pairs demonstrate positive slope, negative slope, zero slope, or no slope at all? So I'm not saying that all 8 of these points lie on the same line. I'm just picking 2 that lie on a line in 4 different examples. So for question A, we would say something like this, that the slope, and I might even use a subscript here, the slope of question A is equal to, let's take our y values and subtract them. We'll take 4 minus 7, that looks like the y2 minus the y1, over negative 2 minus negative 3. I'm going to use parentheses here just to separate the subtraction signs. And 4 minus 7 is negative 3. Negative 2 minus negative 3 is like negative 2 plus 3. that equals 1. So the ratio is -3 divided by 1, and that simplifies to -3. We have a slope of -3. The slope for question B would be done similarly. We'll subtract our y values, so 1 minus 1. Oh, that's interesting. And then we'll subtract our x values, -4 minus 3, y2 minus y1, and then x2 minus x1. That's going to produce 0 on top divided by -7 on the bottom, and that's going to reduce to 0. So points in part B produce a slope of 0. All right, so how about the slope for part C? Similarly, y values, 1 minus -3, 1 minus -3, divided by x values, 7 minus 7. Now this produces something that's kind of interesting. That would be 1 plus 3, or in other words, 4. And 4 over 0, because 7 minus 7 is 0. That produces an undefined result. We can't take the number 4 and divide by 0. We'll talk more about that in just a moment. I'm running out of room, so I'll calculate the slope for D down here. The slope for question D is our y's subtracted, so 4 minus 1, divided by our x's subtracted, 8 minus 5. And you'll notice in all of these examples I went in the same order. I took y2 minus y1 and then x2 minus x1. That's the order that was described in our equation. Now this numerator turns into the number 3. The denominator also turns into the number 3. And we get a slope equal to 1 when those are divided. All right, so I think we've got the slopes for all of these, and I'm pretty happy with the answers. My next question is, does the order matter? Now let's take option D for just a second and decide if order matters. What if I didn't subtract 4 minus 1, and what if I had subtracted 1 minus 4 instead? Well, would I get the same answer? If I subtracted 1 minus 4, well, that's going to look like a -3 to me. So 1 was my first y value, and 4 was my second y value that I subtracted. But you'll notice that this y value of 1 is corresponding to an x value of 5. So if I write 5 and subtract the 8 in that order, well, now I end up with a -3 again. And coincidentally, and actually nicely, we see that -3 divided by -3 does also produce a +1. So the order doesn't matter as long as you're consistent in both directions. Where we might run into a problem is if we go out of order for one group, but in a different order for the others. So if my y's got subtracted, let's go back to the original, 4 minus 1, in that order, but then I subtracted my x values, 5 minus 8. Now that's going to be a problem for us, because now we have 3 over -3, and that's going to reduce to -1. That answer is incorrect. The slope between those 2 points certainly is not -1. We could verify that with a graph if we need to, but the point here is that while order doesn't usually matter, we do want to make sure that we subtract in the same order relative to the coordinates that are provided. So, does order matter? I would say not too specifically. I would say it this way. I would say that it only matters in that you must subtract in the same coordinate order. If you pick from this first coordinate and then subtract the second coordinate, that's okay. If you pick the second one and then subtracted the first, that's okay. But you don't want to mix and match within the x's and the y components of each coordinate. Now, as far as where is there a positive slope, negative slope, and so on, well, I think it becomes a little bit clearer. We have a positive slope with this example down here. So question D had our positive slope. We had a negative slope here in question A, negative slope. And then we had a 0 slope here at question B. So those produced positive, negative, and 0 slopes. And interestingly, we would say that there is no slope here for question C. and that's because our calculation came out to be undefined. What's important to note is that a slope of 0 and a slope of undefined or no slope is actually different. 0 slope and no slope are different. We can see that difference here in this chart below. This chart does display what a positive, negative, 0, and undefined or no slope looks like. This is the one that we would call a positive slope, and we call it positive because the line rises from left to right. We read our graphs much like we would read a book from left to right, and as we move from left to right, we see that the graph actually increases in height. Its y values increase. This one we call a negative slope, because as we again read from left to right, we actually have our y values that are decreasing. So again, moving from left to right, our y values reduce. Negative slope. Now this example here, this third one, is what I would call a slope of 0. This has a 0 slope. Now I would say that this has a 0 slope because it doesn't rise or it doesn't fall at all for the horizontal motion of the graph. There is no rise and there is no fall, so therefore it has a slope of 0. Maybe more clearly I would say that it rises 0 or it falls 0 within the horizontal run. In this final example, we say that there's no slope at all because it has an infinite rise, if you will, for no horizontal distance change. And when we define our slope as rise over run, we can't have a number on the top with a 0 on the bottom because that division by 0 is always going to produce an undefined result. So, long and short of it is this: horizontal lines have 0 slope or a slope of 0, whereas vertical lines have no slope at all. And lastly, other lines that have positive and negative slopes are described here. Now we've talked about the slope of lines. Let's talk about an equation or a way that we can represent an entire line with a linear equation. There are several different linear equations that we will learn about, and one of them we will call the slope-intercept form. We call this the slope-intercept form because within the format we can actually identify the slope and the y-intercept of the graph. The numbers that we put in place of an m and b value are indeed the slope and the y-intercept. So the format looks like this: y equals m times x plus b. Now we've already talked about the m value representing the slope of a linear equation. This b value, the number that replaces the letter b, is often called just the intercept, but more clearly this is a y-intercept. It's not an x-intercept, but a y-intercept, where the graph will touch or cross the y-axis. So as long as we have a line that is not vertical or horizontal, there will always be two intercepts, an x-intercept and a y-intercept. And while both can be helpful, the one that we'll use more frequently in our exercises today is going to be the y-intercept itself. We're going to be interested in where the graph touches or crosses the y-axis, and from that position, if we establish our slope, our rise and run, we can then regenerate or create the entire graph. So, with that in mind, here's an example. What's the equation of the line if the following information is given? Well, we have an m value of 1/5 and a y-intercept at the coordinate 0, -3. One last thing before we actually complete this. If you think about all of the coordinates that have an x value of 0, those will be coordinates along the y-axis. So, in other words, all y-intercepts must be reported as a coordinate with an x value of 0 and a b value reported in the y position. So you might think of y-intercepts in that format, 0, b. Now as far as the equation goes, this is pretty straightforward. We know that y is going to be equal to mx plus b, m times x plus b, and in this case we have an m value of 1/5. A b value, I'm going to call that -3 because that's the number in position on the coordinate. So we can write 1/5 times x plus -3. Or better still, if you don't like the addition of a negative number, we can call this y equals 1/5 x minus 3. Now I can actually plot that on this same graph over here. So I'm going to erase some of these notes and do that. I would like to start with the y-intercept. It's easier for me to pick a point to begin with and then graph from there. So I have a y-intercept of -3, and I have a slope of 1/5. So I'm going to rise 1. I'm going to run 5. I'm moving to the right. We always try to move left to right if we can. If I rise 1 and run 5, that puts a coordinate right here. And I'll be able to connect those 2 points with a straight line. And I think, let's see here. Oops, that didn't quite work. Let's try that again. So here we go. All right, I think that looks pretty good. So that line now represents the linear equation y equals 1/5 x minus 3. And here we had a non-vertical and non-horizontal line in the first example. Same thing in the second example, and you notice that they've intersected or crossed one another at about this position. So that's something that we'll talk a little bit more about in a few moments. What about example 3? Can you determine the slope-intercept form of the equation that's represented below? Well, again, we need an m value and we need a b value, and according to this diagram, we should be able to find both. I'm going to start with the b value. Here we have a b value of -3. Some might want to report that as a coordinate, and I'm okay with that. I actually like that idea. We might write the coordinate as 0, -3. The y-intercept is actually a point, not just a number. Now we have a slope that we have to worry about. Now there are 2 points that are already given to us here, and I'll just go ahead and use them, but any 2 points that are on the line will generate the same fraction. We would want to pick 2 points that fall on what I call lattice marks, where these points of our graph grid lines come together. If you try picking a point that's not on a lattice mark, it might be kind of hard to tell where that point actually sits. So it looks like I have a run of 2. I'm running horizontally 2, and I'm rising. This is kind of counterintuitive here, but I'm rising a -1. I'm actually dropping. I'm falling 1 unit. And so we can indicate that fall by using the number -1. So if I report rise over run, we have a -1/2. It looks like we have an m value, or a slope of -1/2, and a y-intercept at -3. And therefore we can report our slope-intercept equation as -1/2 times x minus 3. Now we do have other linear equations known as the point-slope form and the general form. We sometimes call that the standard form of a linear equation. And each of these equations can be rewritten into point-slope form by isolating the y variable. Here's an example of an equation in standard form, we call it. Can we rearrange this into slope-intercept form? And I would say yes. We just have to get this y value by itself. So if I recognize that this y value, this variable, should be isolated, I have to work backwards through the order of operations to do that. So our order of operations is PEMDAS, and to isolate I should work backwards. So that tells me if I can add or subtract anything away from this y, I should do that first. So I notice that I have an entire group of 5x. I'm going to subtract that entire group of 5x from both sides of the equation. I'm going to keep this equal sign present, and 5x, take away 5x is going to cancel. We're left with -4y. And on the right side I have 16 take away 5x. These are 2 unlike terms, so I can't combine them together. I would not call this 11 or 11x. I have a whole number 16 take away 5x's. Those are unlike one another. They can't be combined. And we might write 16 minus 5x, and that's technically okay. But I'm actually going to report this a little bit differently. I'm going to call this -15. I'm sorry. Sorry about that. -5x plus 16. We had a positive 16 here, but a -5x that can't be combined. I'm going to write it in this order because that looks like a slope-intercept. That looks like a slope-intercept equation to me. And I just caught myself here. I shouldn't have used point-slope form here. This is a slope-intercept form that we're going after. Sorry about that confusion there. This is a slope-intercept, not point-slope form. Please make that correction if you're in your notes if I don't correct that before handing that out to you. Okay, let's resume. So we almost have y by itself. We're still trying to get y by itself. We've completed an addition or subtraction step. Now we can consider multiplication and division. Can I isolate this y value by using some sort of multiplication or division? And the answer is yes. I can divide both sides by -4. Now it's important to note that everything on the right side gets divided by -4. So that's a lot like taking the -5x and dividing it by 4. And also taking the 16 and dividing it by 4. When we report this final answer, since we prefer to have slope written as a ratio or fraction, we'll often write this as -5/4 times x. That's perfectly fine. And then the math here works out nicely. 16 divided by 4 is indeed 4. So while the standard form of the equation was provided to us up here, we've actually transformed it into slope-intercept form, not point-slope form, slope-intercept form, and now this is something that I think I could graph a little bit more easily. The format back here was a little bit difficult to see. We can try another example, this time with fractions involved, but the process is effectively the same. We're trying to isolate our y value. That's how we will report our answer in slope-intercept form. And so if we would like to isolate the y value with an equal sign in the problem, then we have to go backwards through PEMDAS. Is there any addition or subtraction that we can utilize to get this y or y group by itself? I think yes. We can move this 3/4 x to the other side by adding 3/4 of an x to both sides. Here again, these will cancel from the left, and we have 1/2 y equals, again, two unlike terms. They can't be combined together, so I'm going to report this in what looks like a slope-intercept form, 3/4 x minus 1. So now we're still trying to get y by itself, and I've completed the addition and subtraction step, so I want to consider the multiplication and division step while working backwards through PEMDAS. We could divide both sides by 1/2, and that would work, but I'm going to choose to multiply both sides by 2. If I multiply by 2, that's going to cancel out our 1/2. So I'm just going to make a note here that I'm multiplying both sides by 2. The 2 times 1/2 cancels, and we're left with y equals 2 times 3/4. Well, that becomes 6/4. 2 times 3/4 is 6/4, which would then reduce to 3/2 x, and -1 times 2 is -2. And we now have a slope-intercept form of this equation. If doing the mental math is a little bit difficult for you, please do remember that I permit the use of a calculator in most cases, so we can check our math this way too. I probably wouldn't write the entire expression into our calculators, but if we multiply piece by piece, we'll see the results that I think I just reported. So 2 times 3/4, 2 times 3 divided by 4 would end up being 3/2. If I wanted to show that exactly the way it was written on paper, we might write 2 times and then control divide 3/4. And press enter, and we get the same results. We got 3/2. And of course, -1 times 2, checking ourselves here, is indeed -2. So we've got 3/2, x, take away 2. I'm pretty happy with that result. So let's finish up this video with a real-world example and then a kind of check your work problem. We have an equation, y equals -1/15 x plus 4. That equation is going to represent your distance in miles from home. So y, the dependent variable, is the distance in miles from home for each minute that you walk. the minutes or the amount of time that you walk, is x, our input variable. So question A, if you graph this equation, what would the slope represent, and what would the constant term 4 represent? Please explain. So if I'm thinking about question A and I'm considering just a rough sketch here, I know I have a y-intercept of 4 and a slope of negative 1/15. Now, there's a negative sign in front of the 1/15, and if you recall from just general arithmetic, the negative sign could mean negative 1 over 15. It could also mean positive 1 over negative 15, but it does not mean negative 1 over negative 15. There's only one subtraction symbol or negative symbol. It could go to the top or the bottom, but not both. So I say that because that kind of helps us understand the behavior of this function. We can rise negative 1 and run 15 and create another point on this graph. Or we could rise 1 and run negative 15. To rise 1 and run negative 15, that would be like going up 1 but left 15 units. In either case, the data points, I think, would fall in a straight line, and we'd have a nice sketch of what that graph would look like. Okay, so with that in mind, we've graphed the equation. What does the slope represent? Well, again, x is the time that we spend walking, and y is the distance from home. What does this slope of negative 1 over 15 represent? Negative 1 over 15 represent. Think about it for a second and write down an answer. Pause the video now and check your work in a moment. So if we think of slope this way, I might say something like this. For every 15 minutes of time, or every 15 minutes of walking, we're actually going to reduce the distance from home by 1 mile. And if you answered with something similar to this, I think I would be pretty happy. We might also recognize that we have our y-coordinate distance divided by time, distance divided by time. For those of you that are familiar with this equation from your science classes, distance divided by time produces a rate, or we might note that we're moving at 1/15 of a mile per, not hour, but mile per minute. And so I think that would be an acceptable description of this slope as well. Now, because the slope was negative, I would indicate that our rate is negative 1/15 mile per minute, and that would take a little bit further of an explanation, but I think if you have an understanding of that, then you're in pretty good shape. For part B, are you walking towards home or away from home? Well, if the distance is reducing, or if we have a rate of negative 1/15, if the total distance from home is reducing, if it's got a negative rate here, I think we are walking towards home. We could say that we're walking towards home, and I know that because the distance from home is decreasing. Now, interestingly, at some point this graph will reach 0. After a certain amount of time, the graph will reach 0. The distance will be 0 from home, and that might mean that you're at your front door, but if you continue traveling on that graph or on that path, you might move past your house, and the distance would then start to increase. But that's more of a question for science class, the difference between distance and displacement. We'll certainly save that for another time. And lastly, we have a classmate that states that the equation 2y minus 4x equals 10 has a slope of 4. Do you agree or disagree, and why? I want you to think about this equation for just a second and think about your responses. You can pause the video now to work on it and resume playback in a moment to check your work. So I think we should say that we will disagree with this student. While it looks like 4 is the slope because 4 is the number that's paired with the letter x, what we have to remember is that slope is only shown in slope-intercept form. This equation was not in slope-intercept form. We should isolate the y in order to make that happen. So while doing so, to isolate the y and working backwards through PEMDAS, we add 4x to both sides. We would still need to isolate y then by dividing by 2, and after we divide this side of the equation by 2, we're left with a slope-intercept formula of y equals 2x plus 5. So that tells me that in this case the slope is actually 2 and not 4. I hope that clarifies a few things, and if you have further questions, of course, please ask. Reach out to me in class or by email or a message through Schoology, and I'll try my best to respond as soon as I can. Thanks for watching.